Welcome to this conference presented by CMG and MVS Solutions. We're privileged today to have John Baker speaking to us. He's had over 20 years in IT, which I find hard to believe as I've known him for a while, and he still looks pretty young for 20 plus years. He's currently the Principal Z Performance Specialist, but has spent many years doing exactly the kinds of things he's going to be talking to us about, such as putting in WLM goal mode and GDPS data mirroring. Has much experience with performance analysis tools and techniques at all levels. He's assisted many of the world's largest data centers with their ZEOS performance challenges and has done a lot of work for CMG. So without further ado, let's hear John Baker tell us, why did my job run so long?
Thanks, Denise. Thanks everyone for attending today. Yeah, why did my job run so long? And thank you for that very nice introduction. Yeah, 47 and holding. Let's get right into it. Fairly short agenda today. Really, we're just going to talk directly about, firstly, where is my application spending its time? If you read the abstract, this is really kind of at the heart of what we do in performance. Whether you're talking about driving to work, which might take you an hour, or you're talking about how long your job ran, which could be 5 minutes or 5 hours, what you want to understand is what we call the distribution. So again, thinking about driving to work, it's maybe I drove, it took me an hour to get to work, but how much time was I moving? How much time was I sitting at stoplights or sitting in traffic? And when I was moving, what was my average speed? And what's the distribution of that? Was I doing that average speed most of the time, or only part of the time? So we break that down in the system as CPU time, I/O time, and various wait times, and there are a lot of them. Then we'll talk about what am I waiting for, the flavors of queue time, and this is really more at the system level. If you're on the application side, there's not as much you can do about this, but this is more for the system folks, and what can or should I do about these delays. And then we'll have some fun at the end. I'll give you some real-world comparisons about what this looks like in our daily lives. Should be lots of time at the end for Q&A, so please hold your questions. We'd be happy to answer. So first, let's look at what we call the distribution of elapsed time for an application. And this can be a batch job, this could be a transaction, it could be any unit of work that's running in ZOS, or really any computer system for that matter. The principles are not that different. Your total elapsed time is going to be the combination of your total CPU time, the time that you spent using the CPU, the total I/O time, which is how long it took you to read and write from disk or tape or other auxiliary storage, and the total wait times. You know, if you're waiting for the CPU because it's too busy, or if you're waiting for disk because it's in use or it's also too busy, things like that. CPU time further broken down into TCB and SRB time. This is what we call a task control block or system request block. TCB is really what your application is doing. Your program, whether it's a backup, whether it's reading some particular file, comparing some set of numbers, these are the instructions that you write in your application that gets translated to the machine into TCB time for execution. SRB time is time that the system performs on your behalf. So things like IOs, for example, will invoke system services, and the CPU will need to be used, but you're not actually doing that as part of your application. Now on the other side, I/O, that's broken down into four main components: IOS queue, pend, connect, and disconnect time. And you can spend time in each or all of those, and it can seem quite large when you add it all up. We'll talk about all those pieces. And when you talk about queue times, now sometimes when we think about a batch in a system, when we talk about queue time, we think about just initiator queue time, but really a queue is simply a wait of any kind, and there's all kinds of it. Yes, you can absolutely wait for initiators. If there's not enough, you can wait for allocation, NQ. If you need a resource that's already in use by another application, you can wait for system services such as HSM recalls. CPU delay, of course, is prominent, and there's virtually always some CPU delay in a shared environment. LPAR dispatch time, I'll talk about that later on, and that's really key to understanding the performance of your systems, and not always as readily visible or aware. So let's start on the application side first, and we'll take sample job A here. This would be your primary resource for this would be your SMF30 records, where you can measure the time that each of your applications, in this case a job, ran. So I've got a couple of basic metrics here. I've got a total runtime of 4 hours and 23 minutes, a little over 4-hour runtime. Of that, the CPU time was 48 minutes and the I/O time was 9 minutes. So when I just think about this intuitively, logically, okay, I ran for over 4 hours, my CPU time was almost an hour of that, and my I/O time was under 10 minutes. So really, it's not practical for me to look at the I/Os. I'm not going to waste any time saying, oh, well, is my storage well-tuned? Am I accessing too many data sets? You know, having any problems like that? It's really not going to help you much, since of the 4 hours, I only spent 9 minutes doing I/O. I want to focus on the CPU time. So how do we do that? Well, reducing CPU time, again, this is really on the application layer. One of the first things you can do, and it may seem simple, but sometimes we neglect these things in ZOS because things just run, recompile. IBM is constantly updating and improving the compilers, the COBOL and C compilers and others that run in the systems. And ZOS 1.13, 2.1, 2.2 coming soon. All of these improvements can improve the runtime of your jobs, but you may not always take advantage of them. I know some of my IBM colleagues point this out all the time. For your application to take advantage of improvements that IBM has made, you need to recompile your application. And then, of course, you can tune the application. There's lots of good performance tools out there. Most of you are probably familiar with Strobe. It's been around forever. There are many other tools such as FreezeFrame and other brands that perform a similar function. These are tools that will sample your job or your transaction as it's running and essentially measuring, much like the SMF data can do, but at a far more granular level, tell you what area of your code is spending time using CPU. So then you can take that back to your developer, and there's that last point, you know, you want to make friends with these guys if you're on the system side, because if you're the system administrator, the performance or capacity person, you can run Strobe and say, all right, I can see that your program is using most of this CPU time is in this area of code, but it's really going to be then up to the developer to look at that area of code and say, all right, well, how can I improve the efficiency of that? Let's look at sample job B. This job ran for just under 3 hours, 2 hours, 41 minutes, and 30 seconds to be precise. I've got just over 20 minutes of CPU time. I've got an hour and 37 minutes of I/O time. So now this seems pretty obvious. Conversely here, unlike the first job, there's not going to be a lot of value in tuning the CPU of this application. I ran for 2.5 hours or so, and over an hour and a half of that was on I/O. So in this case, I really want to focus on that I/O time, find out where it's being spent and what can be done about it. Now, to reduce I/O time, you want to first break it down into the patterns, and you can get this from the tools I mentioned before, such as Strobe. You can also get this from SMF42 data is extremely valuable. If you're looking at VSAM, SMF64 records are extremely useful. These will tell you, for example, the patterns of I/O. Is it sequential versus random? Read versus write? Buffering, it seems obvious, but sometimes we forget these things. Maybe we set buffers on our jobs long ago and that worked just fine, but if the amount of data or the way that the data is accessed has changed, you might want to revisit that. If it is a VSAM file, you want to know, do I want to use NSR or LSR buffers? And that will be largely determined by if the data is accessed sequentially or random. So answering that first question. Sort's a big one. It's always popular. You have to be careful. Sort likes memory, obviously, but I would caution you against giving it the world. I have seen it, and I'm sure many of you that have been around have some horror stories about applications taking over, and if you know the nature of MVS, you can't kill MVS by running the CPUs through the roof. It'll just keep chugging on forever and ever and ever. But if you starve MVS of storage, it will come to a screeching halt very, very fast. Address space create failed, auxiliary storage shortage, nothing's going on, you're in big trouble. So, balance your memory use. Block size. You have system determined block size, and generally that works well. But when you look at that, it'll tend to make really big numbers. I would say still check. Just a couple of rules of thumb that I would offer here. If you're sequentially accessed, make it half track. There's no reason for it to be smaller than that. The channels are quite fast these days. 27,998. That's going to work. It's going to help for size too, because you're going to then get 2 blocks for every cylinder. You're not wasting space. And for random, again, revisit some of your vstem files from days gone by. We used to make the index really, really small in these things, and that made sense with SCON channels or slower technology. You wanted the data transfer size to be as small as possible, so it might be 500 bytes, for example. There's no point in making a block smaller than 2K on a FICON channel. Without getting too much into that area, but the long and short of it is FICON uses a unit of transfer we call a data information block, and that data information block is 2K in size. So if your data is 500 bytes, that just means it's going to have another kilobyte and a half of gas in that block. So there's no sense in making it smaller than 2K. Compression. There used to be a large debate about compression. Should I compress my data? Well, that's going to use a bunch of CPU, and CPU is expensive. I don't know if I want to do that anymore. IBM's come out with the enterprise data compression cards, and these things look really cool. You plug this into your, I believe it's also available on the EC12, but certainly in the Z13, and it offloads those compression cycles. So your general processor is no longer going to chew MIPS to compress your data. You can go ahead and use your normal SMS compression instructions. It'll offload that work to the ZEDC cards. It's going to cut down the number of IOs, the number of transfers that go to your storage. It's going to cut down the amount of space that you use. Sounds like a really, really good deal, and I think it's reasonably priced. Now I sound like I'm advertising for IBM. And finally, I'd just say include the storage subsystem in your capacity planning. We do capacity planning for CPUs all the time, but do we size our storage appropriately, or do we just say, well, I need another 100 terabytes or whatever the number is? You should actually also consider what the performance capabilities of that hardware is. All right, so that was applications. Let's talk about queue time, getting back to that sitting on the highway business. You drive to work every day and you're thinking, well, geez, it's the same distance. How come yesterday it took me 25 minutes and today it took me an hour and a half? Well, this is the reason. The distance didn't change between your home and your work, and the average speed that you would try to do is not going to change. But these queue times can vary based on a number of factors, and let's take a look at some of those. So this is kind of the scientific view of what we were just looking at with the car traffic, and the queuing theory. Math people in the world will get this intuitively and probably take it even to another level of detail. But at a high level, what we're really pointing out here is how utilization works. As utilization increases, your overall response time increases, and the key word here is that increases exponentially. Does not increase linearly. See the blue line at the bottom? That's your execution time. So if you're in the supermarket and you're in the checkout, and say there's such a thing as an average number of items, you can say with a reasonable degree of confidence that the same checkout person that's scanning your items, because now that's all they have to do, it's a lot easier, can check you out in approximately the same amount of time. What's different is how many people are in line. So this isn't changing the speed of that person that's checking you out. It's simply changing the amount of time that you're in the store, and that's relative to the number of other people in the store. This, again, for the queuing theory folks in the call, this is what we refer to as Little's Law, a fellow back in the 50s that discovered this very simple and yet powerful metric. So point being, when you reach very high utilization levels in a computer system, up to 100%, your wait time becomes so high that it's not really very practical anymore. You're going to be spending far more time waiting than executing. Now there are various flavors of queue time that we can see and we can measure within our computer system. The first one, I'll call this waiting for a server, if you will. So a batch job, this is waiting for an initiator. Kicks transaction, application owning region, IMS MPRs. And I think our instinct, again, in days gone by would simply be, well, I'll just start more. I mean, why wouldn't I just do that? Why wouldn't I just start more initiators, start more AORs, start more MPRs? That way I won't queue waiting for them. That may not necessarily be a good idea. Next, CPU delay. We used CPU and we were looking at the application example. Now we're talking about how long do I wait for the CPU? This is very much like that checkout scenario again. How long do I have to wait because of the people ahead of me before I get to get checked out? And this is as measured in the RMF records, and here we're talking about type 72 records at the service class level. This is waiting for the logical CPU within your LPAR. We'll contrast that with the physical in a minute. I/O delay, we talked about using I/O. Well, you also wait for I/O. You can I/O's queue time, pen time, disconnect time, still there. Interesting nomenclature since FICON channels never actually disconnect, but we still use the term. Capping delay. If you are using caps, if you're using soft caps, this can be reported, which is very useful when you're looking at your RMF data. You can independently report how much time was I delayed because I hit the cap versus how much time was I delayed just because the CPU was too busy. Those can be reported separately. And an interesting point here is an LPAR can be capped, but your application may not be delayed. And that just depends if you're actually requiring more service than the cap allows at that time. And those metrics are reported independently. Again, very useful. If you use WLM resource groups, they can come with a minimum and a maximum. Maximums are a popular option. Uses the same algorithm, same technology under the covers as LPAR caps with what we call awake and sleep slices, where your resource group, when you reach that maximum, again, it's going to limit your consumption. And finally, waiting for what I'll call logical CPU to be dispatched. This is, of course, within our machine, we have one or more LPARs on a physical machine. So I can first wait for my logical CPU within my LPAR, and that's governed largely by my service class in WLM, but besides that, I may need to wait for Prism to dispatch a physical CPU to my LPAR in order for me to actually get service. And that's governed by primarily by the weight, demand from other LPARs, and the overall capacity of the machine. So first, let's look at the Initiator Queue. And just for your reference here, I've given you the actual variables. SMF records start with the numbers that are kind of short for the record type. So R723, R72, this is a type 72 record. This is a variable within the type 72, which is a service class related level, WLM service class. And that variable reports the total queue time. And I point out here in parentheses that you want to divide this out because this is over the interval for that service class period. What is the accumulated queue time for all of the work? If you want to get the average queue time, you got to divide that by the number of units of work in the service class. Again, our instinct might be, okay, well, if I'm waiting for initiators, just start more initiators. And again, I would say that's not necessarily a good idea, particularly today. The quote I have at the bottom, if you've been to any of my presentations talking about processor cache, the nest, relative nest intensity, all that kind of good stuff, that quote is taken from the IBM LSPR, and it's a link at the bottom. And this is just one of the things that we can do to reduce our RNI and improve performance is to reduce the number of simultaneously active address spaces, and specifically this refers to initiators for batch, for example, kicks, AORs, and IMS MPRs, as I mentioned earlier. Having too much concurrency in your system can make that system thrash and lower your actual productivity level. You may have seen this chart as well. We've used this as an internal benchmark that we ran here at MVS Solutions to essentially prove that theory that IBM puts forth, which is, too much concurrency is a bad idea. And in a nutshell, if you haven't seen this before, what we did was we took 1,000 jobs on an isolated LPAR, isolated machine, all running the same service class, and submitted them through a scheduler, steady state of submission. First ran them using WLM initiators where they're completely unrestricted, and WLM will continue to start more and more initiators in response to the queue because it doesn't like that initiator queue time. The problem, of course, is you end up with 300 concurrent address spaces and the system's running overloaded, and things are not moving along very well because the jobs are thrashing. And of course the benchmark in that case takes over 10 hours to complete. Then we ran using our automation, and the key to this automation is that rather than automatically just letting a job start whether there's an initiator or not, we first check what is the utilization of the machine and what is the velocity and performance index of the workload. Is it performing well? Are the delays, CPU delays, acceptable or not? And is the utilization not too high? And we factor in all of these things every 10 seconds and make a calculation whether we should, how much work we should start, how many initiators we should run to maximize throughput. And for the most part, you can see it's stuck down at around 25 concurrent address spaces. And the results are quite clear and quite stark. The entire work runs over an hour sooner. The green line also shows the number of jobs that were completed using the automation technique compared to the wide open initiators. So you're actually finishing work faster. You're having 25 concurrent address spaces in your system versus 300. This is really just a no-brainer way to operate. Okay, CPU delay. Talk about CPU delay. This is one of the more common ones. Now, first of all, I want to point out you're almost always going to see this. Don't think that you can look at your CPU delay for your applications and have none, unless you had, absolute dedicated processors, dedicated memory, dedicated network and storage, and only one application running. Then you might approach a level of zero delay. It is a shared environment after all. There are multiple processors, there are multiple applications, so you're always going to see some degree of CPU delay. Now, what's the definition of that? From a SRM or WLM perspective, that simply means that my work was ready to run, but it's delayed, and it will accumulate delay samples and report these in that variable listed there. This is related partly to the actual service class, the goal, the importance, which translates under the covers, of course, to your dispatching priority within the system. Higher priority works will generally have less delay as it has a first crack at the CPU, if you will. Again, though, as I point out, there's always some. And then the tolerance is really subjective. What can your applications tolerate? What can we as human beings tolerate? If I'm putting a letter in the mail to send to my grandma because she doesn't have a computer, I have a degree of tolerance of days. I know that she's not going to get that right away. If I'm at a restaurant and I want to pay my bill and I got a babysitter at home that needs to get home in 10 minutes, I want to tap my card and I want that transaction to run in seconds. So that particular type of work has a much lower tolerance for delay. Really, it's up to you. Are your goals or your SLAs being met or not? I point out as well at the bottom here, priorities are relative. Overloading leads to thrashing. Quite often, I find in many cases we're guilty of saying, well, something is experiencing delay, so I'll just increase the priority. I'll increase the service class of that, and oh look, somebody else is having delay. I'll increase them, and so on and so on and so on. If you put everybody at the top of the food chain, of course, what you end up is just thrashing because the CPU just says, well, okay, I'm going to try and serve all of these guys, And what he's going to end up doing is giving very small time slices to each unit of work and not actually completing any, very much like the benchmark you saw earlier. And finally, just as a recommendation myself, I'd say if you're not using it already, consider discretionary for mean time to wait. Some think on the face of it, well, why would I want to use discretionary? That's kind of low priority. Well, remember, again, priorities are relative. So as long as you don't have a whole bunch of work up at the top, you're not going to crush the work at the bottom. And mean time to wait is a really powerful way of running work. I won't go into the details of it, but long and short of it is, if you're CPU-bound work, you will tend to float to the bottom. If you're I/O-bound work, you will tend to float to the top. And the methodology behind that is it reduces the overall delay for all of the work running in the service class. If you only need the CPU for a second, I'm going to let you have it, because I know you're only going to take it for a second, then you're going to let go. Conversely, if I know you're CPU bound and you're going to hold that CPU for a long time, meaning nobody else can have it, I'm going to make you wait a little bit longer so the other work can get through. That's mean time to wait. It's a chart of some actual data just kind of illustrating what we're talking about correlating. And this is one of the things you want to do when you're looking at all these different data types is to correlate. You know, when I see something that's high, well, what does that mean compared to something else? So what we're showing here, the black line is the utilization of the system. The colored lines, the green and red and blue, are the CPU delay for 3 different priorities of applications. As you can see, I've called them high, medium, and low. The green high, red, medium, blue, low. And what you can see, you know, looking at the left there, when the machine gets fully to 100%, the CPU delay for the applications are really intolerable. The high is doing okay. He's about 35%, but again, depends. If that's a tapped transaction, that may even be too high. What is the toleration for that? And certainly for the medium and low, we're 90+% CPU delay. That's really a complete waste of time. You've got applications here that are just not moving at all, running at this level of utilization. The system would actually be healthier if they weren't in the system at all. So really you want to control that utilization. And conversely, you see that 50% delay marker. If you go over the actual chart, it's actually running at about 97 or 98% utilization. So you can still get very close to 100 and do well. It's when you really get flat out that things, again, go bad, like the exponential chart I showed at the beginning. I/O delays. 3 primary flavors. As I mentioned at the beginning, there's 3 components. There's connect, disconnect, append, and IOSQ. I don't mention connect time here because it's largely considered productive time. It's the definition of when you're actually transferring data, but there is some protocol overhead as well. If you see very large elongated connect times, it might be worth looking into. But primarily you want to look for these things. IOSQ time. Now in this day and age, everybody should be running hyper-PAVs, parallel access volumes. If you're not running those on your storage controller, you're probably still seeing IOSQ time. And I apologize, as my dog would like to say hello to everyone. Pen time. Pen time has a number of subcomponents. You have CMR, or command response delay, and this primarily indicates an overloaded controller. This is, in network terms, this is the time from the initiation of the I/O from the channel on the CPU side until acknowledgement comes back from the storage controller through the directors to say, yes, I'm ready to accept an I/O now. That should be very, very fast. This is network speed and processor speed. So if that's taking a long time, you definitely want to look into it. Or device busy is another component of pen time. Don't see a lot of this anymore. This is volume contention. This is largely solved with not TAV, excuse me, multiple allegiance. I forgot the term. It's been around for so long because it's built into every modern controller today, but it essentially handles the serialization of data within the controller. Essentially that as long as 2 applications are not trying to update the same record at the same time, they can go. It means you can read at the same time, and you wouldn't have that. If you do see a lot of that, it probably means you've got a hardware reserve. one LPAR holding onto a volume with a hardware reserve and another LPAR looking for it. If there's any remaining time, because you get a total pen time, you get these subcomponents, this is likely channels, but that's pretty rare in a FICON environment. You see this all the time with SCON. Finally, disconnect time. Again, unless you're 100% write, which should be cache hits, or 100% sequential read, where you're going to pre-stage data, you're very likely going to see some disconnect time, and these are primarily your random read misses. So as fast as your hardware might be, you've got these massive databases, and if I need to read a record from some obscure account that wasn't found in cache, it's got to go back to that old spinning disk, and it's got to get it. And the fastest spinning disks in the world at 15K are still going to take you 3 or 4 milliseconds. Even a solid state disk is going to take you a millisecond before that gets done, which at processor speed is actually pretty slow. So you're going to see some of that. Or a sync remote copy. If you're doing that, you will see disconnect time on your writes, because there'll be 100% cache hits on your primary controller, but now you have to wait until that write goes to the secondary controller, gets stored there, gets acknowledged back to the primary, and then you get channel end, device end. And no, as I've been heard before, we have not made much progress in improving the speed of light between controllers. Sorry, a little funny there. So let's revisit sample job B, just for fun. We've got our runtime, 2 hours, 40 minutes, 20 minutes CPU, an hour and a half of I/O time. So let's break that down a little bit further. That hour and a half, what is it? These are, again, variables from the SMF30. I've got delay time, wait time. What this is referring to is a disconnect time. So of that, an hour and 37 minutes, I've got 40 minutes of disconnect time. That's 40% of the total. That's pretty significant. And if I divide that out by the number of IOs, EXCPs, or execute channel program, I get about a 0.263 millisecond average disconnect time. On the face of it, I'd say that's reasonable for random reads, but again, you want to decide, what kind of workload is this? Is that expected or not? If you need to improve that, the point there, maybe you want to consider a solid state for that particular workload to eliminate that disconnect time, or at least reduce it. Again, it could be a sync copy as well. The main point here is you want to become familiar with what are the typical response times for your applications, so then when you see outliers like this, you go, well, is that expected or not? Capping delay. Well, obviously you don't have capture, you're not going to see any of this. If you do, there's a couple of variables that you want to keep an eye on. And this is, as you can tell from the numbers, SMF70. So this is from the SMF type 70, your primary CPU record. The NSW variable says that the CPU has been capped, the LPAR has been capped, by Prism, because WLM told them to, because in this case your rolling 4-hour average would have exceeded the soft cap limit. This will delay Prism from dispatching physical CPUs to the LPAR. But another variable that you really want to focus on is the NCA, which is, was work actually delayed for CPU? Because you don't really care about the CPU being dispatched or not if your work didn't need it at the time, and I'll illustrate what that looks like. This is where I would have to throw a shameless plug in there for Throughput Manager automation. You really wouldn't have to worry about this as much if you were using some of our functions. So this is kind of what this looks like. What I've got here is a chart, 3 LPARs. The one really, the big production one, is the green. That's doing all of the demand for the work. The black line across the top there at 800, that's the cap. So this installation has a cap in place. And the red line is the rolling 4-hour average for the machine, which is the one that really matters. It's the one that you build on. You see what happened as the rolling 4-hour average exceeds that cap level, the LPAR becomes capped. And at the same time, I can see that work is delayed because I can see that the work is pushing up against that actual cap. Now, to be fair, it's difficult to tell if the work is actually delayed or does it just barely need that amount. Well, that's where you look at that variable and say, am I showing delay cap delay samples? Because that says, yes, the work would like to go higher as it did before the cap, but it can't. You'd see at the end of that section, the work is no longer delayed simply because the demand for the work has dropped off. By, looks like the 6 o'clock interval, we see the green and blue bars dropping down beneath the cap. The demand is not there. Now, the cap is still on. You can see at the top bracket, and the reason for that is because the rolling 4-hour average is still above the soft cap limit. And these are the rules put in place by IBM when you do soft cap, which simply means that the demand will be limited to that cap level for that period, should the demand be there. But that's the difference between those two variables. Just pointing out here, because this was from an actual production site, is that capping can impact all workloads. I think there's another, shall we say, myth out there where we think that, well, you know, as long as I've got my priorities right in WLM, I don't have to worry about capping because my important work is going to be fine. It's only the low priority work that's going to be impacted. And that's simply not true. When Prism caps an LPAR, it's not aware of the specific work that's running within the LPAR or the priority of the service classes of that work. That's not its job. It simply says you've exceeded your rolling 4-hour average cap level, and I'm now going to reduce CPU access to that LPAR indiscriminately. So if it is a high priority work that is next to be dispatched, and we get what we call a sleep cycle, which means that Prism is not going to be dispatching a physical CPU during that SRM interval, then the work will be delayed. And this is what the chart shows here. This is an importance 1 workload, and we can see that when capping begins, this is charting the actual velocity of the workload, and the goal is at the top, 90, which, you know, as an aside, is probably a fairly aggressive workload, perhaps unrealistic. But that WLM is unable to meet that goal. The velocity drops down significantly during capping because WLM can't do anything about it. It can put you at the highest priority, but that's only within your LPAR. If the LPAR is not being dispatched, you're going to wait. Resource group max. These actually, as I think I mentioned earlier, use the same technology as LPAR capping with wake and sleep cycles. They can be useful. You can put service classes into a resource group and say this is the max I'd like you to have, whether that's unweighted service units across a plex, or that could be a percentage of an LPAR, or it can be a ratio of CPUs, and it will cap the work within that, within the resource group, and this will override the service class goal, be clear. So even if you have a high importance workload in a resource group, it will be limited. And you can track that with the variable there back in the type 72 records that says number of samples when the resource group maximum was enforced. So this is useful if you are using resource groups and you say, well, am I actually hitting my limit or not? You can check. And finally, I think this is probably the biggest one. LPAR dispatch delay, I'll call this. And really what this is the ratio of logical processor busy to physical processor busy. And this is not always as obvious, but it's very, very common. It's been around for a while. It's talked about maybe in different ways. I have to give, you know, full shout out here to Kathy Walsh. Back over 10 years ago, she did a paper at Share, introduced the term short CPs, the Washington System Center. That's the link to the paper from the IBM Washington System Center, still very, very valid. What she was pointing out there was primarily related to CICS transactions and how they can experience delay when Prism does not dispatch the LPAR as often as you would like, very much like I was showing in the previous example with the high priority workload. Barry Merrill, always helping us out, created this variable here, PLC PRD ready queue. It essentially calculates that ratio for you of logical to physical busy. And when you see a gap between those things, well, then you know you've got a problem. This type of problem is improved with hyper dispatch, and I know Kathy would certainly recommend if you're using IRD, the Intelligent Resource Director, that will help. This is an illustration of that phenomenon, I'll call it. What I have here is the blue lines representing the number of initiators that are active during the interval. This, by the way, you can get this data all from your Type 70. And then I've got the two lines at the top. The green line is MVS busy. So this is the logical utilization of my LPAR. The red line is CPU busy at a physical level. So these are the physical CPUs that are allocated to this LPAR, and of course they're not dedicated, they're shared with other LPARs. But this is the amount of service that Prism is delivering. So if you want to think of it as the green is like demand and the red is like supply. And for a lot of the times, you can see in the left and the middle of the chart, they overlap each other. And that's good. That's nice, healthy environment. Supply and demand is matching and life is good. When there's a gap, as we show here, now my demand is all the way up to 100%. My supply is as low as 60%. I've got a 40% delay. And again, this is completely irrespective of what the priority of your workload is. Your LPAR is experiencing a 40% delay in being dispatched. And the point at the bottom there, you can't just fix this by starting more initiators or increasing the priority. It's not going to fix that problem. So let's just take a little trip in the real world of what this looks like. I always like using the deli counter. I talked about the grocery store before, but this is kind of a fun way that I like to illustrate things. So how many can come into the store at any one time? Can I, in a computer system, can I affect this number? Yeah, I could make more space in the store if I wanted to. What's that? That's initiators. I could start more. Is that a good idea? Perhaps not, but I could. If I wanted to let more people in, I could let more people in. Who's next in line? Well, what's that equivalent to? Well, in the daily counter, that's you get a number. We talked about that before. Well, what if I just increased it? Well, what if I said in the daily counter, well, gee, everybody's waiting too long. I'll tell you what, I'll just give everybody number 1. Will that help? No, that won't help. I'm going to thrash. I'm going to have a whole bunch of people all at the counter at the same time. I still have the same number of servers at the counter. They can't serve all these people simultaneously. Nobody's going to get done. This is equivalent to your service class or your dispatching priority. Now once I'm at the counter, okay, so now how long until I get to give my order? Well, this is my logical processor busy. That guy behind the counter, he's the logical processor. And there are probably more than one of these guys. You probably have more than one logical processor within your LPAR. And if you have enough of them, you could add more logical processors, although hyperdispatch will cut you back, which is a good thing. But you could do that, which would get you to the counter. Getting you to the counter, of course, doesn't get you your sandwich and get you out the door. This is what gets you out the door. I know, the ever-popular slicer. These are your physical processors. So if you think about that counter picture where, you know, maybe I've got 3 or 4 or 5 people at the counter, but maybe I've got only 2 or 3 slicers at the back. Well, let's put this picture together. So I could hire more people at the counter, but I only have 2 or 3 of these slicers, so I can have a lot of people that I can take their order, but even the people behind the counter, they have to wait to get to the slicer to make my sandwich. And that's access to the physical processors. And I guess the point I'm making here is exactly what we do in our systems is we just keep pushing. You know, we add more initiators, which causes us to have to increase priorities when application screens, which causes us to add more logical processors, which causes us to do what? Causes us to make IBM happy because we got to upgrade. And we keep going on this deadly circle. And what I'm suggesting is that really we need to step back and look at the entire picture and manage our resources a little bit better. And then we won't continue on this deadly circle of just essentially throwing hardware at the problem. So, how have I gone? Hopefully I haven't gone too long. Before we wrap up, any questions, thoughts?
Actually, John, there are some good questions.
Cool. Questions are good.
The first question is, people have been asking for copies of the presentation. Is that possible?
Yeah, absolutely. We can send that out, and I'm pretty sure. You know, I checked with Dave at CMG, but I think they put that out on the site. But certainly, if for whatever reason someone doesn't get it, we'd be happy to email them a copy.
Great. The first technical question is on the slide, utilization versus CPU delay. It shows better balance overall on the right side of the chart.
Utilization versus CPU.
Quite a ways back.
Oh, there it is. Yes. Yeah, it does,
The
doesn't it?
question was, what changes allowed this?
It's very subtle. It's a great question, and you know, I didn't even think about it because this is just real data. It's subtle, and what it really boils down to, without taking into account other variables, but with what we have in front of us, it's the utilization, the black line at the top. Notice how it's getting high, but it's not quite at 100%. It's amazing what that small amount can be. And sometimes this depends also on your capacity. If you have a box with one CPU and that CPU is used, is effectively 100% busy. If you have a box with 10 CPUs and half of them are used all the time and half of them are not used at all, your average utilization is 50%. But what we really have, what you have is 5 CPUs that are 100% busy, 5 CPUs that are doing nothing. So the point I'm making here is that in any box with a reasonable degree of capacity, even a small dip in average utilization means there are very likely CPU resources available. And because of hyperdispatch, it really boils down to the individual CPU's availability. So I would directly point that to running just under 100%. And if I can throw out the shameless plug, this is exactly what ThruPut Manager automation does by not starting work unless there is sufficient resources available.
Our next question is regarding I/O delay. In your experience for modern subsystems, do you see more pend or disconnect as a cause for delay?
Wow, that's a great question. Well, of course, now people might laugh, but you know the universal answer, it depends. What those two metrics point to are primarily areas, two separate areas. So pen time, probably the most common cause of pen time would be command response delay, and that's more related to the overall capability of the subsystem today. So, I mean, the CPUs are very fast, the channels are very fast, FICON director is very fast, that's not an issue. What you really want to measure at that level is the overall throughput of the storage controller, and that's not necessarily easy to do. I know this is kind of a long answer. But you want to measure the megabytes per second that are going through the controller, not just what they say in the distributed world, IOPS. IOs come in various flavors. It's not really that representative of how hard the box is working. The number of megabytes that are passing through a controller will correlate in the same way as the amount of CPU time does on your machine. And essentially, when that controller starts to reach 100% utilization, just like a computer, you will start to see CMR time. Disconnect time is more largely a factor of the application. If you have a lot of random reads within the application, then you're going to see more disconnect time, and usually there's no black and white fix for that. If the application can't be changed, you're going to be throwing memory at it, you're going to be throwing solid-state disks at it. Sorry, that was really the answer.
Your next question is, what do you generally see as the cause of delays in batch jobs today? Logical resources or physical resources?
Physical. Yeah, it's physical resources. This particular chart is probably one of the most common things that I see in environments large and small. And it's not obvious, because if you're just looking at, you know, how long is my job running, again, back to the title, how many initiators am I running, what's my MVS utilization, that only gives you a partial view. You really need to look at this area right here, this gap, which is, you know, is the machine able to provide, able to meet the demand And this is where you really want to be smart about things, because if you're not able to meet your demand, sure, you can just say, give me a faster machine. You know, that's an option, but that's an expensive option. You're likely to get some pushback from your management on that. You want to look at the consumption of the applications and the business priority of the applications. I mean, this example here, we can see we've got some pretty big peaks, and then we've got some valleys. So does everything need to run during those peaks? Is there work here that can be deferred, slowed down, run later? Those sort of things are what I'd look at.
Your next question, if I am currently meeting my response time requirements, is there any reason for me to look into delays?
Well, I guess you'd say from a business perspective, no. What I might look at is there an opportunity to save money? If I'm currently meeting all of my SLAs, the instinctive thought might be, well, I guess there's nothing to do. But if you're easily meeting them and you have cost pressures, as most of us do these days, then you might want to take a look at, you know, do I need this much capacity? Maybe I can use some caps if I'm not already, or I can lower them, or I look at some ways to reduce consumption, save money. But I guess to the actual question, I would say not if you're meeting your applications. Now, of course, I say that, and then I think, well, are you expecting growth? If you're expecting growth, it might still be a good idea to do that investigation and look for your delays, because if your workloads grow and you have some delays in there, maybe they won't start to show up until your volume goes up. So it might be nice to be aware of them before if you need to make changes.
Several people have asked, where is the link for the slides to download that you're alluding to? You're saying that's on the MVS Solutions site?
I'm going to check.
Or is it on CMG?
I think we might need to check with Dave. I'm not sure logistically how that works with the CMG folks. But
I believe
by
we
all
can
means,
send it out to everybody.
Yeah, I certainly have no problem at all. Dave's posted yeah, I see Dave is posting the CMG website there. You know what, I'm going to also, my email, I think, if it's
I think you're at the end, yeah.
There it is, yeah. You can always email me. I certainly have no problem with emailing anybody directly, the slides.
One person made a comment, I was in mainframe performance and tuning back in the day. I used to tune workloads throughput, workload throughput via the SRM. The more things change, the more they stay the same. In this case, what holds up workloads? So my question, do humans still do performance and tuning, or is it now all mechanized?
That's a great question. I wonder if I know the person. I like to think we still do it. I've done nothing but performance for almost 25 years now, and I still enjoy it. You know, it's a really good point. What's old is new again. Way back when we implemented goal mode, the joke went around, oh, well, implement goal mode, you'll put yourself out of a job because the system will just do it. Well, that's not the case. And we also know the basics of if you remove one bottleneck, well, you're just going to find another one. So really, there's never a shortage of need, you know, to find efficiencies. We know this intuitively, both technically and in business. You know, we're always being tasked with, is there any way I can find more efficiency in my system, in my application? Is there any way I can run faster? Is there any way I can reduce costs? You know, this is why I work at MVS Solutions. This is what ThruPut Manager does. It's what I've always done.
Okay, your next question. In the checkout counter example, will it also depend on the number of items to be checked out per customer? Does it help the system to have increased priority based on the number of items to be checked out, something like checkout counters at Walmart with less than 20 items?
Yes, and that's a great analogy. I love that you are going along with my checkout. Yes, certainly, and that's, you know, you might contrast that with the mean time to wait algorithm in discretionary, where, you know, the workloads that consume less CPU will automatically have greater access to the CPU. That method will overall improve the throughput of your system by reducing the total delays, exactly as you described with with a checkout method. You know, in a perfect world, really, if you didn't have priorities, you just dump everything in discretionary and let it run. And it's going to work pretty well.
The next question is, can reduced preemption cause delay, and what is the remediation?
Can reduce preemption. So preemption, of course, is when you're running and the CPU says, well, I'm sorry, I've got to cut you off now. Can that cause delay? Sorry, was the question, can it cause delay?
No, yes, can it cause delay, and if so, what is the remediation for that?
Well, this is really where, you know, I would actually give it back to the system and recommend using something like IRD to balance this, the Intelligent Resource Director. If you're worried about whether you may have provisioned too many CPUs, too many logicals, you know, it'll park the ones that aren't used. There is also a new feature, I'm not sure of the release or if it's out yet, something called Warning Track, which is helpful so your application doesn't get cut off in midstream. This is where the system will warn WLM that the CPU is about to be pulled away so the work can finish. I think that's probably, I'm going to point to IRD for that one.
And that is the last of the posted questions, so we can probably do your concluding statements at this point.
Okay, and I zipped through the slides. Look at me go. Really, it's interesting. We were talking before the presentation. I asked my wife about this. She's a musician. She sings, she conducts orchestras, and I was talking about this technical presentation. I said, I really just want to tell people that it's about balance and harmony, and it's not necessarily technical. And she liked this picture a lot. I guess the point, if anything, that I've tried to make here is that you can't just throw resources at any one area. If you open up too many indicators, you're going to stress WLM. If you put everybody up at too high a priority, then you're going to stress your logical processors. If you configure too many logical processors, you're going to stress your physical processors on the machine. So really, it's balance in all of these things that's going to maximize your performance. That's the idea. Just a quick shout out to MVS Solutions, my employer. If you're at all in the batch world and you're not running ThruPut Manager, you should be, because it does a lot of the things that we talked about automatically. At least that's one application that you wouldn't have to worry about, or application, I should say, workload type, by running ThruPut Manager automation. Running things smart, saving costs with or without soft caps, things like that. Also, I'd point out my email is there at the bottom. You see another email underneath it, systemz at cmg.org. I have graciously failed to take a step back when they were looking for volunteers for the CMG conference this year in La Jolla, and I'll be running the Z track at the conference. So for any of you, if you've got your own stories, if you've got a story to tell, by all means email me. We're always looking for good user stories, presentations, things like that at the conference, and we hope to see you there at the 42nd International Performance Conference in beautiful La Jolla, California. If you've not been, you really should. It's just outside San Diego. That's a great spot to be in November. That is all I had, and thank you again.
Thank you for coming.